Hello there, my name is Ashraf, and today I want us to look at how we can convert a shear force diagram back into a space diagram. So this is our question for tonight, and we are given a shear force. We want to get a space diagram and a bending moment diagram. So join me tonight as we navigate how to do that. So the first thing that we do is to determine a scale. As you can see, we are having 60 meters. We can't draw this on paper. We're also having kilonewtons, which we can't draw on paper. So we need a scale. So I'll determine a suitable scale. And we say to determine a suitable scale, simply get any value here. I'm going to get 60 meters, and I'm going to say I want to represent 60 meters with still 60 millimeters. So if I reduce this, I'll have 1 meter equaling to 1 millimeter. So this is the scale I'm going to use. And then also for the kilonewtons, I'm going to say I'm going to represent the 20 kilonewtons with still 20 millimeters. So that would imply that 1 kilonewton is equal to 1 millimeter still. So this is my scale 2. So I have the two scales. Now I can draw an accurate diagram of the shear force. So simply start off by drawing a horizontal line. Onto this, I'm going to put a vertical line somewhere here. So now, as you can see from the question, this line I've drawn is the middle line in this one. So the distance from down here up to up is actually 26.7. So according to our scale, I'm simply going to measure off 26.7. So 26.7, I'm going to round off and make it 27. So that is my 27 right there. Then going this side, you can see it is 30. And by the fact that this is 60, so that would mean that this is also 30. So I'm going to go this side by 30 and then 60. Then I can see a 7.5 somewhere here. If I round off, I'm going to consider 8 there. Then I see a 15 down here. So that means I'm going to measure a 15 from the extreme end. Then I'm going to slide vertical lines to all these points. Okay, I can now slide horizontal lines, a horizontal line to this point. So this is what I have so far. This, and this. Then I can see that the distance from this middle point up here is 16.7. Using our scale, it will be exactly that. So I'm going to measure off by rounding off and measuring off 17. So I'll come right here and measure 17. Then I can see that going down, I have 33.3. So I'm going to measure off 33.3. And then measure off a 20 from down. So I need to slide horizontal line there. So we have a line here. We have a line here. And then measuring 20 from down, we also have a line here. So by doing this, I have a complete shear force diagram. Okay, so this is positive. Of course, this is negative. Then I'm going to label it with all these forces because they're going to help me derive the space diagram. So this is 33.3 kilonewtons. This is 20 kilonewtons. This right here is 16.7 kilonewtons. And this is 26.7 kilonewtons. Now that we have the complete shear force diagram, we can derive the space diagram. So I'm going to slide a horizontal line and put it somewhere below here. Of course, the horizontal line is going to represent the beam, and the beam will always run from the start of the shear force to the finish of the shear force. So that beam covers the entire shear force. Always, the beam will cover the entire shear force. Now, after drawing the beam, you identify the line that is separating the positives from the negatives on the shear force diagram. And as you can see, that line in this case is this one. This is the line separating positives from the negatives. Perfect. So, where that line starts, and in this case it starts here, and where that line stops, in this case it's stopping here, that is where the reactions are. That's the first thing that you do. You identify where the reactions are. And I'm saying you can only identify where the reactions are by identifying where the line separating positives from negatives starts from and ends. And in this case, I'm saying this line is starting from here and it's ending right here. So at those 2 points, that's where we have our reactions. So our reactions are right there. And we shall see how to determine these reactions using the shear force. Perfect. Now, after identifying where the reactions are, I'm going to assume, this is to make this very easy for you, assume there is a tap here. Assume you have a tap here that is flowing with water. This is a tap. I'm sorry for the minimalistic representation of this, but I'm trying to make it easy for you. Okay, so assume these are pipes. The shear force is made of pipes. So if this is a tap and it's running, by the fact that we have a reaction here, if this water enters here, by the fact that we have a reaction, that means there is a force going up here. That force won't allow the water to go down here. Let me hope I'm making sense. So that water can't go down here. What will happen to the water? It will flow this other side like this. So the water is going to flow like this. And remember, we said every time we see a horizontal line on a shear force, that means there is nothing happening there. So since this water is flowing horizontally, nothing is happening. And then when it reaches this corner, it flows down. Every time we see water flowing down, that means that's a force. So along this line of action, we are going to have a force. And the magnitude of this force is going to be equal to the length of this line. The length of this line will equal to the magnitude of this force. So the length of this line of the shear force in this case is going to be 26 minus 16.7. And that gives us 10 kilonewtons. So this force here is 10 kilonewtons. Why? Because that's the length of this vertical line of the shear force. So water reaches this corner, nothing happens. So it continues horizontally. Horizontally, nothing is happening. So when it reaches this corner, it's going to flow vertically. And we said every time it flows vertically, that implies a force. So we have a force going down here. But where does it stop? It cannot stop here. Why? Because this is the line separating the positives from the negatives. So that implies this pipe here is going all the way through from here up to down here. So the water is flowing from up here, down to this point. So that would mean that this force also is measured from here up to here. So that would mean that I have to subtract 33 minus 20 to get 13.3 as the length of this point, and then add 13.3 to 16.7. So 16.7 plus 13.3, that gives us a 30. So that would imply that this is 30 kilonewtons. Hope I'm making sense. So we are now at this point here. So the water is now flowing horizontally, nothing is happening. We reach this corner, it flows vertically. Once it flows vertically, there is a force. And this, the length of that force is the length of the vertical line, which is 20 kilonewtons in this case. Then the water reaches this point, nothing is happening. Then it reaches this point, then it goes up. And remember, every time it's going up, that's a reaction. So it has to go up to that line that separates the positives from the negatives. So the length of this whole line, that would mean this value here is the value of the reaction here, 33.3 kilonewtons. And then the water is now here, it will go all the way up to this point. And then once it reaches this point, it goes up again up to here. So that would mean that this reaction is 26.7 kilonewtons. Perfect. And this, ladies and gentlemen, is how you determine the space diagram from a shear force diagram. And if you balance out these forces according to equilibrium, we know that the sum of the forces acting downwards must be equal to the sum of the forces acting upwards. So if I add these forces acting downwards together, the number that I get, the sum, and in this case it's going to be 60, has to be equal to the sum of the forces acting upwards. And if you add these, still you're going to get 60. So that would mean your beam is in equilibrium and what you've got is correct. So that's how you check to see if your beam is in equilibrium. Let me repeat briefly for some of my great friends out there. So I'm going to use this here. I'm going to use the original question. So now that you have this, I'm sure you can determine the bending moment diagram. So I'm not going to do this. If you have trouble determining the bending moment, please review some of the previous videos that were lectured here. Now, we said we start off by drawing the beam, and the beam we said runs from the start to the end of the shear force diagram. The beam covers the entirety of the shear force diagram. And then we said after drawing the beam, you determine the line that is separating the positives from the negatives, and that line is purely this one. So where that line starts, that point is this, and where it stops, that point, that's where our reactions are. So the reactions are there. Okay? Then after determining the reactions, I'm saying assume that we have a tap of water, a flowing tap of water here, and assume still that the shear force is made of pipes, and these are pipes. Then I said, by the fact that there is a reaction here, that means there is an upward force in this line here because there is a reaction. That force is repelling the downward movement of water at this point. So what happens? The water travels horizontally. And we said every time we see a horizontal line on the shear force, that means nothing is happening in that space. So once water reaches this point, it flows vertically. That implies there is a force here. Once water gets to this point, horizontally, nothing. Once we get here, it flows vertically. So there is a what? There is a force. And we said, for the case of this force here, the magnitude is the whole length from here up to here. It's not stopping in the middle here. Why? Because this is the line separating the positives from the negatives. It can't stop there. It has to go all the way through. So once it's at this point, it flows horizontally, nothing. Once it's here, vertically, so there is a force. So once it's here, horizontally, nothing. Once it's here, it flows vertically but upwards. And that would mean that's a reaction. So that would mean this is flowing from here up to that line separating the positives from the negatives. And that magnitude would be 33.3 for that reaction here. The water flows back here and then up to give us this reaction as 26.7. I'm sure that gives you an idea of what we are talking about. If you still have a problem, try to rewind this back and forth and try to understand the concept. Thank you for watching. See you in my next video.